We have then our next speaker, dear friend, David Sumpter. We try to invite now and then. You started very early in Gothenburg when you were a research assistant up in Umeå, in the northern part of Sweden. And so can we switch to this one? And David is from my old alma mater, Uppsala, where he is having a big group. Some of his former students are here, collective behavior. And lately has been taken onto new fields and, as you can see, written a number of best-selling books. So the title for today here is about fish, about football, and about collective behavior, and most of all, how we can learn from the fish and football about teamwork in an efficient manner. So, thank you, please.
Well, thank you very much. Is it going to go over to my slides? Okay. Well, it's very nice to come here and present this work. Since I started working on football, I've been invited quite a lot to give departmental seminars, and that's because they want to have something which everybody can relate to and is interesting to a wide audience. They're sort of, when you have these departmental seminars, as everyone knows, quite often people go a long way into depth into what they do, and they present the equations, and nobody understands after a few minutes. But everyone can understand football, so it's very easy to get. And today, I think this is meant to be a popular thing, and we've had these very nice popular things, and I think I don't have a single equation in my talk. You'll either be glad or horrified to hear. But I'm going to go a little bit through my progress from working on fish to working on football. And I've got this idea, because fish, in a sense, they're a team. Football is a team. And the idea is, can we use maths to understand those types of teams? So I've worked on fish for a while. This is from a BBC documentary. And this is the way we should think about fish schools. These are various fish schools shown in this video, but you see all of these fish interacting with each other, creating these amazing collective patterns. You see this rotating ball of fish here, and then in a minute, when the predator comes in and attacks the fish school, they can move in uniform away from the predator attack. And so I think in this video, we're about to see a seal, I think it is, come in and attack the school. And as it comes in, maybe a few of the fish see the predator coming in. Here's the seal coming in. And they all manage to move away from it. And they basically do that by following each other. Each fish can see about 5 or 6 fish around it. It can sense, in the case of these fish, it can sense via the lateral line how they're moving. And through the transmission of information, they can, as a team, escape from the predator. They can all manage to get away from the predator. In the end, a few of them get eaten, but in general, this is a better way of escaping the predator when they move together. Now, oh no, there is an equation. Okay, sorry, I have to give up. No. It's a discrete time equation, so it doesn't count. Okay. And there's an alpha there as well. That's terrible. They're using Greek letters. Okay, so this is, I think Daniel was here and spoke to many of you last week. This is a model that was developed by one of my PhD students. It's not randomly selected because I selected it because Daniel did his PhD with me, but there are tens of thousands of models of how fish-like particles interact with each other. And this is one of them. And his model is quite simple. The idea is you have an interaction rule. I'll even point to the equations. And what this tells you is that you have a direction you're already moving. You continue in that direction. In case it's not clear, these are fish. I drew them. So I'm not sure if everyone realizes they're fish, but these are fish. This is the eye of the fish. Fish don't really look like this, but this is a fish. And this is the direction it's moving. And that's this D. And then there's the direction of its neighbors. They're up here. There's a vector pointing towards them. And the fish adds up those two vectors, and its new vector is a weighted average of those two, and it just moves off in that direction. Now, there's a sort of twist in this model, and it's that these modeled fish have a blind angle, so they can't see the fish behind them. And that's actually not true. Fish often can see 360 degrees, but they see things better in front of them than they see things behind them. They react more strongly to things that are in front of them than behind. So that's the model. The position is updated just based on this directional movement, and then we see what happens. So I'm actually going to simulate these fish in 3 dimensions, and I've actually added a little bit of a variation as a repulsion term, but I'll get them both going. Yeah. So this is 2 different parameterizations of this model. They're moving around in 3 dimensions. This is the physicist's representation of a fish. So biologists think that these fish are swimming backwards because it's not the head. This is the head is at the back, and then the red thing is the vector pointing to the direction they're moving. And you can see they produce 2 different shapes. This is a kind of moving animal group. This looks a little bit like a bird flock, actually. So not so much fish, but the movements you might see if you looked at some crows flying around in the evening or starlings moving. You see these collective motions, and they're moving together in the same direction. This is more like what we saw in the video. You have this milling, 3-dimensional, rotating shape where the fish move around together. And the point here is that it's very simple rules. If we go back to Daniel's slide, there was very simple rules about how these fish interacted. They interacted only with nearby neighbors, yet they were able to produce these very complex motions. So simple interactions together produce very complex motions. And these simple interactions are, of course, caught by mathematical models. So I mentioned here as a sort of aside that there's 10,000 models, there's 10,000 papers published on these types of self-propelled particle models. And then, of course, all the mathematicians are deriving continuum approximations, and there's like loads and loads of work done trying to study these models and find properties of these models. And that's very interesting, but there is a very important question. These models are fun. It's fun that I can have these blind angles and I can show these things moving around. But are they realistic? Can we actually say that these models represent how real fish behave? And it's that question that I've been investigating for the past almost 10, 15 years now. Are these fun models of collective motion realistic models? What we do to investigate that is that we look at the rules of motion of real fish. So this is 8 fish in a tank. These are called mosquito fish, this particular species. And we do a very simple experiment, actually. We just place them in a tank. We watch when they swim around. The colors here are the tracking of the position of the fish, so we have it a few seconds back. And then we look to see how they interact with each other. Do the rules that they are following correspond to Daniel's model or another model or any of the tens of thousands of models that are out there? We can do that by basically looking at how they interact. I'm going to just say a few things about the types of results we found. What we do is when we have this focal fish, we have other fish that are around it. This is the distance to the nearest neighbor. This is the distance to the wall. These are various angles. And what we're interested in is how does this fish respond to its neighbors and to different obstacles that it sees in the way. And what's great about fish is you can just collect loads and loads of data. So now we have sort of 20,000 hours or something of fish data, of fish moving around. We have loads and loads of hours of fish movement data. And we can then use that to build up these types of heat maps which show how they respond to things. I think I'll start with this one. This one says, where is your neighbor? Is it in front of you or behind you? So if your neighbor is in front of you, it has a positive value. And if your neighbor is behind you, it has a negative value. So this is just distance in front in a straight line or distance behind in a straight line. And this is how much you speed up in response to your neighbor. And you see here, if your neighbor is far in front of you, you go very fast. If your neighbor is behind you, then you slow down. You can think of this a little bit like when you're driving a car in traffic. If you see a car in front of you, driving along the motorway, you see a car in front of you, and you feel you have to speed up to be near to that car. As you get near to the car, you don't want to crash into it, obviously, so you slow down. So near to the car, there's a repulsion effect in the opposite direction. And you might, if there's no car in front of you, you might start to go slowly, which is this effect here. It's not as strong as the effect of driving up to things in front of you, but also you speed up if someone starts trying to tailgate you. And that's that effect. So there's a repulsion effect nearby, and there's an attraction effect to things that are further away from you. This is just a three-dimensional representation of it. Instead of just being behind and in front, this fish is actually swimming in this direction, in this case, from left to right, and this is it speeding up to catch up, slowing down, then the repulsion effect in the middle. It's pretty neutral when it's got fish to the left and the right of it. So those are the things that we can do when we have lots and lots of data, is we can start to fit models which really accurately describe fish interactions. I'm going to talk about another thing that we do, and to say something, this is all at the individual level. This is to try and work out what is going on at the individual level. We can also do something at the group level, and here we frighten fish. So each of these blue dots is one tracked fish, and what we do in this experiment is we give the fish a little bit of a shock by shooting out this arm, and we look to see how the fish move away as we shoot out the arm. And this arm has a very strong effect in making the fish change direction. And we can actually break this down. I haven't broken it down. But you can see that there's, if I just play this one last time, you can actually see there's a kind of wave of individuals through. These change direction, and they push all the other individuals till the whole group has changed direction. And a good way of plotting this is as follows. So in this case, the blue, this is the fish plotted. So here's time, and here's distance. So here's the fish traveling from left to right. The blue fish are the ones that are going towards the scary thing. The yellow thing is when the scary arm pops out like that. And red are fish that are going anti-clockwise away from the scary thing. And you can actually see this wave of red fish moving away from it. And as they do so, they make a very compact group. And that compact group changes the direction of all the other fish, and they're able to escape from the predator. Now, that's very like what we actually saw in the first video, where you have this predator coming in, frightening the fish, and they turn away in the wave. So we've reconstructed in the lab how fish interact in the wild. You can actually, and what you can do is you can go back and test this. I'm actually going to talk more about this tomorrow if you come to my talk tomorrow as well. But what you can actually do is you can test these types of models. So once you've got a model, and we built a detailed model of these fish interactions, once you have a model, you can test scenarios. This is, if we frightened 4,000 fish, would we manage to get them to turn away from the predator? And we can show that these waves of turning are actually enough to allow 4,000 fish to, even though only a few of them, only 20 of them have seen the frightening signal, they'll actually make a wave which passes through 4,000 fish. We don't have the experimental arena that's big enough to do this, but we can actually frighten and change the direction of 4,000 fish in a simulation. So that's one of the powers of simulation. You start off measuring individual behavior, you work out what the rules are, and then you can simulate what's going to happen in a very large group of fish, and you can work out how they transfer information between each other. I think it's nice to pause a bit to think about what we do. And this is, once I'd spent a lot of time studying, I've studied fish, and I've studied ants, and I've studied birds, all different types of species. And it's nice to sort of take a pause and think about what is it you do as a mathematical modeler. Well, what you do is you follow a modeling cycle. What I started with when I started my talk is I talked about a global pattern. how the group as a whole moves, the collective motion of these fish in the sea. Then I told you all about Daniel's model and the theory-driven explanation. Then I started to do experiments on an individual level. Then I start to simulate my individual level model and see if I can reproduce the level. And then I can go back and compare to the observe the global pattern. We haven't done the experiment in the seas yet, but we can start to see a reasonable model of how fish move and why they're so good at swapping information and so on. And it's this cycle that we tend to look at in all of the different types of systems we study. Whenever we study fish or we study birds or whatever we study, it's that type of cycle that we go round to improve our understanding. I made this slide recently of... because that's... I have this problem that I can't... I'm going to have to switch that off because this is the experiment we did on these people and the sound is still on it. Anyway, what I wanted to do is I wanted to show you, I said there's this sort of methodology that we use where we go through this modeling cycle. And we've done this on lots of different systems. Up in the top there is this is cicada calling. This is an example where we actually recorded the volume of cicadas in the bush in Australia. This is actually this is one of my postdocs' parents' house, and we ended up recording the volume of cicadas. We listened to them in the evening calling, and we ended up taking microphones and placing them out. And you can actually see that there's a traveling wave of sound. So a large red thing is how large sound it was. And I was very interested in this disease spread thing just now because we actually haven't quite got a complete hand on understanding the modeling of these types of systems. And it really is the same type of spread that you see. One cicada starts going up, and you also have this periodic thing like these seasonal outbreaks. So you can see that type of spread of noise. I've already talked about the spread of information in fish and turning. This is ant trails. The ants leave some trails and they follow each other, and we look at how the structure they're built. This is an example on a larger scale of ant trails. We went out in the forest and measured stackmyror in Swedish, wood ants. We measured their trails and how they were structured. We looked at locusts, which go across the desert, how they make these vast swarms, because there you have a swarm of locusts is many kilometers across, but there's only individual interactions on a centimeter scale. Looked at chickens, looked at homing pigeons. We looked at sheep and sheepdogs. This was a study where we looked in extreme detail at prawns in a bucket. And there we could actually get to the real detail of individual interactions. We filmed, I don't know I know the biologist who came up with it, but I don't know why Ashley came up with this idea. But he decided he wanted to film prawns in a bucket. And we spent years analyzing how prawns move around and interact with each other in buckets. We now have a very good model of prawns in a bucket, if nothing else. And from prawns, we can go all the way up to, we've looked at things like human crowds. And this one I don't want to start because the volume comes on for some reason. This is a study we did of applause. And this actually, again, goes back to the SIR model, because we showed that the SIR model can be used to fit how people start clapping after a seminar. So one person starts clapping, then it spreads to more people. And interestingly, and unlike disease, there is an infection in the recovery. So when you recover from, you will stop clapping if other people stop clapping. And so the more people who've stopped clapping, the faster the recovery, and it drops off, making a more symmetrical shape, actually, than the one that you have in the original SIR model. So you can actually use those types of models to look at clapping. This was one we did on people's staring behavior. And this was also, we've looked at concerts and crowd behavior. So I've been working on all of those systems, but I also have a hobby. And my hobby in recent years has been this. The kids in black here, this was 2 or 3 years ago. They were about 9 or 10 at the time. The kids in black are my son's playing in this team, and I coached this team in my spare time. And I wasn't like a total football fan to start off with. I was kind of had a vague interest. But when my son turned out to be very interested in football, I got very interested in it myself. And so I'd be looking at those videos of fish and prawns or whatever during the week. And then at the weekends, I'd be not always looking at videos, but I'd be looking at live at stuff like this. And so, and it's a very similar problem. You've got a team of people. In this case, we want our black team to move apart from each other, spread out, and to occupy the whole pitch. And we want to try and understand how they should move best. And we want to explain to them simple rules by which they can interact with each other and play better football. And that turned out to be just as interesting scientific problem for me as the problems I was studying with animals and so on. How can you actually understand the collective motion of football players? And also around that time, I decided I wanted to write a popular science book. And first of all, I wrote to an agent in London, and I described all of the stuff about the animals. I described how exciting it was with the birds and the ants and so on. And he wrote back and said, well, yeah, you write well, that's nice, but nobody's interested in animals. But you wrote that one thing about the football. Can't you write a book about football instead? Everybody loves football. Write a book about football. And first I was quite insulted by this, but then I thought, this is actually a really interesting challenge, to take what's essentially my hobby and apply my scientific understanding to that hobby. And I started to think more about it, and one thing I immediately thought, well, the starting point has to be slime molds, of course. How many of you have seen slime molds? Yeah, not even half. Okay, everybody should know about slime molds. Slime molds are the most amazing thing. Slime mold, I mean, I don't even know properly what they are, but they're like amoeba-like they're not animals, amoeba-like organisms. And this scale of this is about so far across. And what they do, this is the slime in the middle, and this is oat flakes. Slimes love oat flakes. And what we've seen in this video is they spread out and they make connecting branches which connect up all of the oat flakes. So from this central position, they've actually made a network that connects every one of those oat flakes in quite an efficient manner. Is a very efficient connections between them. And what my colleagues Toshi Nakagaki and I worked with Toshi, but this was a study he did a bit before we started working together. What he showed was that he'd actually placed out these oat flakes like the suburbs of Tokyo. So the central point there is center of Tokyo. This is the airport out here. This is Yokohama down here. And he'd placed out each of the oat flakes proportional to the population density of various suburbs around Tokyo. And he'd found that the slime mold had found a very good solution for connecting up these oat flakes. The solution was so good, in fact, that it could be compared to the Tokyo rail network that the engineers had made. So in terms of efficiency, for robustness of this network, and also for directness, the amount of train track you'd used, the Tokyo rail network created by the engineers was as good as the one created by the slime molds. He's repeated this experiment in several countries, actually. He's found that the German rail network, slimes managed to find exactly the same quality of solution as the engineers. French rail network, they did exactly the same. Slime managed to compete with the engineers, make a good solution. But the British rail network, there the slimes found a better solution than the engineers had for connecting up everything in Britain. I think it's actually been better in Britain since they did the experiment. Maybe they've learned from the slime. But the slime is very efficient at producing these types of solutions. Okay, so what's slime got to do with football? Well, you'll have to bear with me a bit, but first we'll look at some football. Here's some football. So when you're a mathematician, you know that the first thing you have to do if you want to understand a system is you study the perfect example of it. This is mathematical perfection on a football pitch. This player here is Lionel Messi, who is by any statistical measure the best player ever to have played football. There's no real serious debate about that. And this is the Barcelona team of 2010-11, which is possibly the best club team that has ever played football. And I think before I started thinking mathematically about football, I would just follow Messi in this case. I would see, well, this is amazing. He's basically dribbled past the entire team and created a goal from nowhere. And Messi is the most amazing football player. But there is actually a few other things you should look at. And in particular, if you look at, that's Xavi and that's Pedro. And just have a look at their motions for a bit. And I'm actually going to analyze, not Messi, but I'm going to analyze what Xavi and Pedro are doing. What they're doing, this is now a bird's eye view of the football pitch. This is when Messi first gets the ball. And you see that Xavi is standing right in the middle of the opposition players. And what I've done here is I've drawn, this is a Voronoi diagram. Every point in each segment is the nearest point to Xavi. These are all the nearest points. They're nearer to Xavi than any other player. These points are all nearer to Messi than any other player. These points are all nearer to Iniesta than any other player. And so I draw the Voronoi diagram of the positions of all the Barcelona players in grey, and then I look at where are the opposition players. And if you look closely, you'll see that the opposition players are stuck on the edges of the Voronoi diagram. So they are furthest away from any other player. And what Xavi does, which is so clever, is he moves basically into the middle of all the other players, and he creates space for himself. And in doing so, he creates this nice Voronoi diagram. And the lovely mathematical result there is that the jewel of the Voronoi diagram is the Delaunay triangulation. And this triangulation gives a lovely passing possibilities for Messi, Xavi, and Iniesta. In this case, he takes Xavi, but he could easily have taken Iniesta. And it makes a very efficient teamwork. And if you look at Barcelona from that time, that's what they're doing over and over and over again. You can plot these Voronoi diagrams, plot these Delaunay triangulations, and you see that they're continually creating these things. And I often get the question, surely Barcelona aren't, it's not that Pep Guardiola, who was the manager at the time, he doesn't say, yeah, Xavi, could you stand there so that you create a Voronoi diagram that the opposition on the edges of? Because, of course, if you do that, you'll get the Delaunay triangulation, and then it will be a bit easier to get through the opposition. It's not that they give those explicit instructions, but they do a lot of training exercises which allow them to create space. And those training exercises mean that it comes automatically for the players that they can create these types of opportunities. You see here, this one is a few seconds later. Pedro does the same thing. There's a lot less space in this case, but he finds his central point, the triangulation is created, and the next pass can happen. And so when you look again at these videos, you see this. Now Xavi goes in the middle. Pedro just takes that little step into the middle away from his marker, and each of those moments allows them to make the perfect pass back to Messi and create the thing. And everything about what was called tiki-taka football at that time involves that type of motion. And you can look at this in a different way. This is a passing network for Barcelona. This is now during an entire match, and it's a Barcelona team from a few years later. What the thickness of each line is how often players pass to each other, and the blue position is the average position they are on the pitch. And in that time, this is Barcelona 2015-16, they had a beautiful symmetry. They had Neymar on the left, Messi on the right, and they produced this triangle where they pass a lot to each other, Rakitic, Messi, and Dani Alves. Then over on this side, you have Iniesta, Neymar, and Alba, who were passing a lot in the same way over here. And at the base of it, in fact, the most important player in this particular team was Busquets, because he has connections to all of these things. He can either play it out to this triangle, that triangle, or play it straight out to Suarez. So you can start to get an idea of the symmetry which underlies the teams using methods like this. So I ended up, this is to give some flavor of the different types of mathematical ideas that you can use to study football. And I ended up getting really into this, and I tried to write everything that I knew about mathematics I used to analyze different types of aspects of the game. This is a quote from Paul Gascoigne, Gaza, who's a famous English player from the 90s. known for his great intelligence. And he once said, "I never predict anything, and I never will." And I think this is very nice because this sort of sums up the impossibility of not predicting something. Because goals are very random in football, and that's why it's very difficult to make prediction. But they're so random that they follow a Poisson distribution, which means it's actually possible to make predictions about the distribution of goals. And so it's impossible not to be able to predict anything, as Gaza has shown us here. I looked at Total Cyber Dynamo. That's all about teams which are built on more than the sum of their parts. We see this a lot in ant behavior. As the size of the ant group increases, the productivity increases as a square of the number of ants. And you see that in football as well. As the performance or the contribution of the players, you see this growth. Check My Flow is all about building weather forecasts for players, trying to look where they're passing and trying to understand them using a type of dynamical systems and weather forecasting. I'm going to say something about this world in motion in a bit. I even looked at the crowds. I took in these studies we'd done of applause, and I looked at how chanting spreads in the ground, and I looked at Mexican waves. And for the Swedes here, I couldn't write a book about football without analyzing Zlatan Ibrahimovic. He scored this amazing overhead bicycle kick that every Swede knows about, where he lobbed the English goalkeeper from over his head from a long distance. And so I used Newtonian mechanics to analyze that goal and find out exactly how small chance he had of scoring it, or how much precision he had to score it. Then I did a couple of chapters on this is one on game theory and why you should always play for a win when there's 3 points for a win. And then I also looked at betting. And I think this is sort of important when we think about popularization of science. For many of you who are here, you're going to think that what I've done, I've maybe done a reasonable job. I don't know. Maybe you'll think that I've done a reasonable job of popularizing science. But for the vast majority of people, they just look at what I've just said and they say, yeah, so what? And the reason they say, yeah, so what, I found out after a bit, is because I didn't make any money. There was no financial profit in what I've just done. I just told you some beautiful things about Voronoi diagrams and so on. They only believe that you're using maths usefully if you make money. So I felt I had to prove that I could actually use this to make money, and I created a betting model which beat the bookmakers' odds. And so I showed that it is possible to use maths to make money. It turned out to be the most boring model in the entire book. It was basically bet on a draw. It's really boring. But it actually made some money. And so those are the different aspects of what I ended up writing about with football and maths. Sorry, how long was I meant to talk? Sorry, I forgot.
Sorry, so let's... Yeah, we should roll this. You have 10 more minutes.
Okay, 10 more minutes. Yeah. Okay, so related to this, can you actually make money with maths question? The next question that came up a lot, and this is what I've been working on since I wrote Soccermatics, is I started to get contacted by various clubs, and they would want to know, can we use this maths you're talking about to win football matches? Can we, in particular, they were interested in scouting players. Can we find the next Lionel Messi using numbers? And can we start to win football matches using it? And so I'm not sure I'm going to answer this question yes or no, but I'm going to tell you some of the things that we've been looking at which might be able to, in the future, help you win football matches. So the first thing to note, I think people are very unaware of this simple fact. So what I've done here is I've plotted this is in the Champions League last season. This is the shots by Cristiano Ronaldo. The stars here are goals, and the red ones are block shots, the green ones are misses, where he's missed the goal. What many people are unaware of, because you'll often see, in the evening you might watch a highlight or something, and they'll show Cristiano Ronaldo score a goal from a long way outside the box. You know, he'll turn round, he'll hit the ball with power, and it will go into the top left-hand corner. And that's shown on the news, so people think, oh, Cristiano Ronaldo, he's amazing at shooting from outside the box. The thing is that he misses 29 out of 30 times when he shoots from out here. he is always missing. If you looked at like a reel of all of his shots from outside the box, it would just be miss after miss after miss. And you would never be able to believe that he was like meant to be one of the world's best football players. We've already established who the best one is. He's just somewhere after him. We wouldn't do this. And the point is that the distance from the goal, or basically actually circles emanating from the goal, tell you what the chance is of scoring a goal. And it turns out that even the best strikers aren't very good at converting. It's all about how close they get to the goal rather than how accurate they are when they shoot at the goal. Cristiano Ronaldo is not particularly accurate in front of goal compared to other players. He's just very good at being at the right place at the right time. And that's shown in this picture. There's lots and lots of points where he's taken shots from near to the goal. Some of them have gone in, some of them haven't, but he's always there in the right place. Mohamed Salah, who came rated third, he is further out. He didn't have as many chances as Cristiano Ronaldo in the Champions League last season. He was very successful. He scored a lot, but I'm a Liverpool fan, but I hate to say this, but he was a little bit lucky to score as many times as he did. Ronaldo is more typical, and that's why we rank Ronaldo higher. And so this actually gives a way of ranking strikers. What we can do is we can look at how many opportunities they get and how good those opportunities are, and that allows us to tell how good a striker is. It's a method called expected goals. Then strikers, well, that's good. What about midfielders, though? To do that, we actually look at football as a chain of possessions. We actually fit a type of Markov chain or some sort of Bayesian process to every possession in a football match. This is data from the World Cup final. The green is France and the red is Croatia. Both of them, confusingly, both of them are shooting left to right. Left to right is the standard way you attack in a football data. So they're shooting from left to right. And you actually see the red, Croatia had many more chances that ended with a shot than France had. France won the match 3-1, I think. But they were better. Croatia were actually the better team in the game in the sense that they generated more chances. Anyway, the point I want to make about this is we take a lot of this data. We look to see what's the probability that a pass here results in a shot there. And this gives us a way of assessing every pass. We can actually find out historically what is the quality of a particular pass and also a particular dribble. And this is shown here for Lionel Messi. This is why he is so incredibly good. This is all of his important passes and dribbles in the Champions League. And I haven't shown any player for contrast, but you can see there's lots of them. And he makes lots of passes that are here very close to the box, just like we saw him doing in that video. He makes some longer passes that are valuable. He makes dribbles. And he consistently makes lots of contributions that increase the probability of his team scoring a goal. You can actually go in, if you go in, we've made a website called 12.football, and you can go in and play around with these things and assess the players yourself. We look at, the reason all of these slides are to do with Barcelona, and I'm sucking up to them so much, is I had the honor of going and presenting my research to Barcelona the other week. So I've done a lot of assessment of their players. This is their defender. We looked at all of the stops that he made, and what's very valuable about Umtiti, the defender, is he's making stops a long way up the pitch. He's preventing attacks before they get dangerous. He's making a few stops here, but he's making a lot of very valuable stops up there. And that makes him very valuable as a defender. You can look at why Paul Pogba was so good in the World Cup. This is another measure which I can tell people about if they're interested in later, about where the other team lose the ball. This is actually, I do want to say something a little bit about this. Kante is very famous because whenever he's around, the opposition lose the ball. It's not that he gets it back. He's just this little guy who works extremely hard and runs around. The opposition get very nervous and lose the ball. And you can actually plot that out, and you found that the opposition in the World Cup, he plays for France, in the World Cup, the opposition lost the ball around him more than any other player. And that's why he's so good. He's not a great player of the ball, but he makes the opposition lose the ball. Sometimes he gets in the way, other times he just makes them nervous and they lose it. So he's very good at stressing them, and you can plot that type of thing. And moving on from the fish, and this is actually work that's being done at Barcelona. What Barcelona do is that they look to see how much of the pitch they're controlling. So these are the Barcelona players in the sort of Barcelona-y reddish color. They are moving around here. And all the green and the yellow players are the opposition. The arrows show the directions they're moving. What you're shown here is who controls which areas of the pitch. The green areas are controlled by Barcelona. The red areas are controlled by the opposition. And they actually look at this data, the movement of the players, and they work out how well Barcelona are controlling the pitch. A very nice result that came out of this research is that they found out that Messi controls the pitch by walking. So he doesn't run into areas of space. He just walks very slowly and innocuously into these areas of space. And by doing so, he opens up space for his teammates, because he opens up space for his teammates and also for himself whenever he walks somewhere. And so that's a lot of what he does, is just walking around in a very efficient manner. Then he sprints off with the ball, of course, and scores goals. Then you can do stuff like this. This is a study of 16-year-olds playing football. They're shooting left to right, so this is why there's a confusing thing. They're playing on half a pitch, 8-a-side football. And one thing we've done is we've looked at synchronization in this case. And the green links here, they mean that the players are synchronized with each other. So the yellow team are synchronized in the up and down direction as they move in defense. When the yellow team get the ball, they become blue. That means they're anti-phase correlated with each other. And then when they lose the ball, they go back into this synchronized defense thing. So this is the type of thing you can use. That guy's not synchronized. You can actually use to spot if somebody's not working hard enough in defense. If they suddenly get a blue arrow on them, that means they've become unsynchronized with the rest of the defense, and you can see who's not doing their job. You can also find out who the leader is, who's the most important player in these types of groups. We can also look at vision of players and what opportunities they create and so on, and how they can play through a team. Whether here he has an opportunity to play there, and a top-down view allows you to find out the different opportunities that players have and create, and to start to build up some sort of understanding of these rules of interaction. And I think with that, I'll say thank you, and you can ask me any questions you have. Thanks.
Any questions?
These pictures you show of the dots on the football, are they taken by some aerial photographs, and then somebody has analyzed it?
Yeah, that's a really good question. So
Can you repeat the question, David?
Yes. The question is, how is the data collected for the movement of the football players? So the data is collected primarily that they film from like 8 or 9 different angles in the ground, and then they use a tracking methodology to follow the players' movements around, and they can get the data with that. But it's not quite as simple as that. It doesn't work that well. They also have 2 people who sit there, and these are computer games players, and they actually note everything that the players are doing, if they're passing the ball, if they're doing a dribble, and so on. And so they then put those 2 data sources together in order to get a full picture of the play. Now, in this 12 football thing, which you can go in and look at, we just have the data of the on-the-ball actions. We don't have the off-the-ball actions in that data set. So there you can see all of the passes and so on. The data of the movement of the players off the ball, which I showed in Barcelona, for example, they're owned by the TV rights people, and they only give them to the football clubs, and they don't allow researchers to work with them, which is it's a bit annoying for open research.
I have a question, David. Thank you very much. It was really interesting. And the Voronoi diagram that you pointed out, have you also added this aspect of that they have different velocities?
Yes, in fact, I should have said that, because that's exactly what the Barcelona people did.
Heat map there.
That heat map is basically a Voronoi diagram which accounts for the velocity of the player. So the arrows you see there are the direction they're moving in, and you see, if you look at that yellow player, he doesn't have control over the pitch behind him so well, and that's because he's running backwards like that. And so that's the sort of thing that you can, just the movement. So if a player who's out there can move back all of a sudden, that player's still working there, then you've got a sort of attacking opportunity. The best place, because you can also, I also mentioned this sort of rings that come out of the goal. The best place for this player to get the ball is either there or there at this particular moment, because there's no player who can get to that before a Barcelona player can get. So it's a sort of extension of the Voronoi diagram, which allows. So I joked at the start that Pep Guardiola wasn't using Voronoi diagrams. Barcelona now are using a more sophisticated version of Voronoi diagrams in the analysis of the game.
So I have a question. So you probably are aware of this movie, Moneyball.
Yes.
So is anybody using the same principles for football?
They're trying to some degree. So Arsenal were one of the first clubs that really got into that. They all have, like, you know, one sort of stats person working for them, but I don't think any of them have really invested in it in a proper way. Whenever I've talked to clubs, they want to do it really cheaply. It's quite interesting. Football clubs don't have much money. You think that they have a lot of money, but they give it all to the players, and they don't have money for this type of thing. And I think that's sort of balanced towards the skepticism. Is it, you know, if I've got an extra 10 million, will I spend it on Paul Pogba, or will I spend it on an analytics group? And just now it seems that the balance is still, I'll pay 10% extra for Paul Pogba. Whether that will change over time, like it did in the American sports. I think we have these, so I've been a couple of times to sports analytics conferences, and the football analysts, the soccer analysts in the UK, they're so jealous when the American football or the baseball guys turn up, because they get to talk to the head coach every day. They get paid these massive salaries, all of the statisticians who work for them. But the statisticians in soccer are just sort of, yeah, we have to have one of them, but we ignore the person for the most part. It's changing, but that's how it is.
So any other questions? Well, thank you, David.
Yeah, thanks.